Okay, here we are with question 12. As ever, hopefully you've done the question. You may have even marked it. I'm really just going through this just to point out anything extra and remind and sort of top up any bits of knowledge, especially for those of you maybe having trouble interpreting the mark scheme. So I'll let you sort of pause and check you've done the question first, and then we'll get started. Okay, so we've got, this is going to be an atomic or nuclear physics question. Okay, we're told about an atom of gold, which is represented as this, 19779 AU. We're then asked to determine the number of protons in the nucleus and the number of neutrons. Now, this word determine is a little bit cheeky here. Determine usually means do something, work out, right? Now, I've seen this question written slightly different, especially the first one, which is state the number of protons. That literally just means you need to use one of the numbers in front of you. I'm sure a lot of you have got this. It's 79. 79 is the proton number, or in sort of chemistry speak, the atomic number. That tells you how many protons in the nucleus of the atom. Now you notice here you aren't having to do any working out here, but because this is an extended or supplementary paper, they're probably kind of just trying to see if you understand that you don't have to do anything here, right? That all you have to do is really state things. So it's a little bit of a red herring, I suppose, that determine. You definitely have to determine the next one, which is the number of neutrons. That is N, which is your mass number or nucleon number, take away the proton number 197 minus 79, which is 118. So you notice there's 2 marks there. Okay, first one, nice and simple, just writing down the number, stating. In 2, you're actually having to do something. Finally, in part A anyway, we've got a different atom of gold is represented in this way. Notice we've got a different nucleon number. That's because there's more neutrons. And we're given words. Now, you're very rarely in GCSE physics given a nice circle the word question. Here we go. We've got the word ion, isotope, electron, and charge. Now, why have I gone for isotopes? Isotopes, as we all know, are atoms or nuclei with the same proton number but different neutron number, i.e. different nucleon number. We're not ions because we're not charged, okay? We're not charged because these are talking about atoms. Now, atoms specifically are neutral, so I thought it was worthwhile just pointing out here, charge wouldn't work here because atoms are neutral, and that's implied in the word atom, okay? We're then asked to complete an equation for nuclear decay, okay? We are told a little bit of information here. It's always worth your while reading all the bits here. We're told specifically the half-life. As soon as you are told the half-life, I would recommend circling the half-life because you're not told anything for no reason in these questions, okay? I often talk about films with my students and talk about how when you're watching a film, you'll be told information which will come back at the end. That's what the half-life is. This half-life is a number which you need later. We don't need it for part 1. We're just asked to complete the equation. This is beta decay. So we've got gold, Au becoming Hg. This is mercury, I think. Okay. And we know that beta is 0 minus 1. Okay. Now we've got 0 and minus 1. Then that must mean that this is an 80 because 80 take away 1 is 79. We've got a 0 on the top, and so therefore 198 take away 0 is going to be 198. So we get marks here for having the correct symbols and correct numbers. We're then asked about half-life. So this is where the alarm bell should be ringing. You've seen half-life up here. Okay, there's a little callback to half-life. The half-life is the time over which the activity or the number of nuclei of a radioactive or unstable substance reduced by 50%. If I was making this answer a bit better, I realized I probably could put the word unstable here. Number of unstable nuclei. I wrote this very quickly, which you can tell by my handwriting. Okay, the time over which activity or number of unstable nuclei of a radioactive substance reduces by 50%. So it's this constant time which allows 50% reduction. Now, the next question, again, classic question about determining how much of something is left. We are told that we have a sample with a mass of 280, and we're told the mass after 8.1 days. And this is where we're going to use that half-life, finally. The information which was given at the beginning is finally used here. We've got 8.1, and we've got a half-life of 2.7, Well, those of you who can do maths, 8.1 divided by 2.7 is 3. That means there are 3 half-lives. We know from our definition of half-life that after every half-life, we're dividing our number by 2. So if I've got 3 half-lives, I'm going to divide by 2, 2, 2. In other words, I'm multiplying by 1 over 2, 1 over 2, 1 over 2, 1 over 8. My original mass is 280, so I'm going to take 280 divided by 8, and I get 35, which seems fair enough here. Okay, little checks. I mean, you will have done, if you've done something silly here, then you get a bigger number. Right? Over time, we expect the mass to decrease. I'm sure none of you got an increasing mass, and that looks like it's about it for this question. As ever, if you've got any questions, please let me know.